Everyone, this video is an introduction to the normal distribution. So the normal distribution describes a probability distribution that we typically call, in layman's terms, the bell curve. And this is for a continuous random variable where we have the highest probability sort of in the center or around the mean value, and then we have less probability towards each outside. Some key features of the normal distribution are that it's symmetric. It has this peak in the middle, but it kind of tapers off evenly in both directions. And the probability of values approaches zero the further out we get from the mean. So because the normal distribution is for a continuous random variable, not a discrete random variable, the probability of any one value is zero. There are an infinite number of values in a continuous random distribution, in any continuous random variable. And so rather than talking about the probability of, x equals 1 or any particular outcome, we look at the probability of a range of outcomes. In the graph perspective, the different random variable values would be along the horizontal axis. So we're looking at an interval of possibilities. And the area underneath what we call the probability density function, or underneath this sort of probability curve, that area represents the probability of those values. For the normal distribution, the equation for the probability density function is this exponential e raised to the negative x squared type function. Now, if you're not familiar with e exponentials, you don't need to worry about this. We don't need to use this function directly in our calculations, but I wanted you to at least see kind of how we describe this probability distribution. What it looks like is, of course, this bell curve, but the normal curve has two what we call parameters, and that is the mean and the standard deviation. So this first graph I have here, this would be the normal curve with mean 0, meaning that all of the values are centered around 0. You can see that the peak in this bell curve is at the x-coordinate 0. And the standard deviation is 1. This mean of 0 and standard deviation 1 is what we call the standard normal curve. We can alter this slightly. So for example, if I change the mean, here on the left, I have a graph where the mean is 2, the standard deviation is still 1. So if I compare these two graphs, they're both a bell curve shape. They have the same sort of width and height and shape, but the mean of 2, the bell curve is shifted over so that the peak is at an x value of 2, and the mean of 0, we have that peak at 0. If I change the standard deviation, I can have these values be either more spread out or more close together. So here's one more graph. This is a mean of 0, so we see the peak at an x-coordinate of 0. And the standard deviation here is 2, so you'll see that the peak is shorter and it's sort of more spread out. It's shorter and wider. With any of these functions and any probability density function, the area underneath the entire curve will always be 1. And this is true for any normal distribution, but also any continuous probability distribution, this probability density function, that total area is always going to be 1. So if we make our data values kind of more spread out, if we look at a larger standard deviation, then that's going to naturally kind of squish down the graph. So it can be more spread out or more close together in a peak, but the normal distribution is always going to have this sort of symmetric peak shape. Another commonality to the normal distribution, no matter what the mean and standard deviation are the sort of the proportions of how much area or how much data or how much probability is represented by different ranges. So this is this graph that I'm showing on the screen is a representation of what we call the empirical rule. So if I consider the mean of my data right in the center, that's right at the peak, if I look at an interval from the mean one standard deviation away, so the mean to the mean plus sigma, whatever those mean and sigma values are, 34.1% of data values will it be in that range. And that's true whether I go to the right or to the left. So we have this symmetry on either side of the peak. So with one standard deviation away, we get 34.1%, or in total, this would be about 68% if we do one standard deviation away in both directions. If I go 2 standard deviations away, so I have the mean plus 2 sigma and mean minus 2 sigma, the total area under that portion up to 2 standard deviations is about 95%. And if we go 3 standard deviations away, I add on this 2.1% area indicated here. The total amount is, I believe, 97.5%, or roughly that. And if we go further out, there's still a little tiny bit of area, a little tiny bit of probability of seeing a value, above 3 standard deviations above the mean or below 3 standard deviations below the mean, but the probability becomes very, very small. So the empirical rule just gives us some general ideas about what proportion of our data we should see in each range, or what the probability of seeing a value in each of these ranges is. Here's a simple example. So women have heights that are normally distributed with a mean of 5 foot 5 inches and a standard deviation of 3 inches. And this data came from ourworldindata.org. It's collected from 20 countries in North America, Europe, East Asia, and Australia. And the question I'm looking at here is, what's the probability of randomly selecting a woman who is between 5'2" and 5'8"? I'm using the online graphing calculator Desmos here for a visual. This represents the normal distribution of women's heights. So the mean of 5'5" is 65 inches, and I've set my mean to 65 and my standard deviation to 3, and the graphing calculator is graphing the normal distribution here. So what this problem is asking is, what would be the probability of finding someone whose height was between 5'2" and 5'8", which is equivalent to 62 inches and 68 inches. This is actually one standard deviation below and one standard deviation above the mean in this case, because 65 minus 3 would be 62, and 65 plus 3 would be 68. So based on the empirical rule, I'm expecting about 68% of data values to fall in here, and the Desmos calculator has given me 0.683. So this means that the probability of finding a woman between 5'2" and 5'8" would be 68.3%, or a probability 0.683. Another example question, what's the probability of randomly selecting a woman who is less than 5 feet tall? This is not going to be using the empirical rule, because 5 feet isn't exactly 1 or 2 standard deviations above or below the mean. But using technology of some sort, we can still calculate this. So I would be looking at, what is the probability of a height less than 60 inches. Visually, what that looks like is, here's 60. This is a little below the mean height. And we're looking at what's the area underneath the curve to the left of 60. This represents the proportion of all women, or randomly selected women. What is the probability of getting someone whose height is less than 60? This is 0.048, or about 4.8%. One last example, what is the probability of randomly selecting a woman who is exactly 5'3"? So again, because we have a continuous probability distribution, my calculator here actually won't let me calculate the probability of exactly 5'3", because that probability is actually 0. So if we think about this in terms of area, 5'3" is 63 inches. We can see 63 inches here, but the area underneath the curve at exactly 63 inches is nothing. There is no area. So you can't actually find the probability of a single value. The way you could think of this is if somebody says that their height is 5'3", it's probably not exactly 5'3", right? There's going to be, a few millimeters or even micrometers off of that. So for continuous random variables, we can't do individual values. But what we might say is, what is the probability that the person's height was, say, between 63 and 63.9 or something like that. Maybe we group together all women who have a height in between 5'3" and 5'4", or something along those lines. So if I went from 63 to 63.9 inches, that gives me an area of 0.104. Again, that's representing this area underneath this curve from the given bounds. And that could be our interpretation of the probability of someone who's 5'3". The actual calculations here, how we find the area, there's various ways to do that. Of course, we could use a graphing calculator like this Desmos calculator. I will have a video showing how to do this in Excel. We can also use this using a z-score lookup table, which is what statisticians would have done before we had computers commonly available. But there are lots of different ways to actually calculate these. I just wanted to give you a sense of what this looks like visually, and how our normal distribution curve can be used for these probability type questions. That's it for this video. Thanks for watching.